bring you along and see what rolls into that. And we're using monitoring of office air quality as kind of like an example, a real-world example, and we're taking you along this journey and showing you what you need to know and what you need to keep in mind when you're doing your own sensor to safety project. Now, the next speaker is every hobby he's ever had has turned up in a business somewhere. He is the head of engineering at DefProc Engineering. Please give it up for the wonderful, the amazing, the one and only Patrick Fenner.
Thank you. So yes, I'm Patrick Fenner, head of engineering for DefProc. We're a design engineering company, so this is all about proof of concept, prototype, small run production, and then being able to take devices onto larger scale production. So being able to create things that don't already exist. That means we pick up lots of different technologies. We've been doing LoRaWAN since, I think, the Things Network's initial Kickstarter in there. But what we're going to go through today is to design a specific IoT solution. I'll take you through the process of that. Now, I am going to use a specific example for that, but really the takeaway is not the decisions that I made as part of that process, or the results of what I did during that process, but the reasons why I went down that road, the decisions I made, and the choices as part of that. First of all, we're going to start off with the requirements. So we're going to need an IoT solution. We're going to need a project to form a solution for. And what we're going to do is office air quality. So being able to make sure that in our office in Liverpool, that we've got enough airflow for the number of people that are in there to make sure we've got fresh air coming in and everybody's comfortable, but not so much that it's drafty and chilly and everybody's just too cold. First up then, that is the requirements, the thing that we need to be able to take and hold in our mind all the way through that process, because it's very easy to get distracted and disappear off and do different things or follow an interest because it looks like it's fun. In terms of monitoring airflow and making sure we've got sufficient airflow for the number of people, we could start by doing things like monitoring the number of people in the space, looking at measuring somehow how much air is coming in or going out. But there's actually a measure in there that we can use a sensor output directly from carbon dioxide. So people are breathing in, breathing out. As they breathe out, we increase the amount of carbon dioxide that's in the air around us. And we can take a carbon dioxide sensor and be able to see not how many people or what the airflow is, but is there the right combination of number of people and amount of airflow? If CO2 is too high, we can increase the air flowing into the room or open a window to increase the air flowing out. If there's too much, we can close those down because everybody's fine. So let's have a look at what CO2 does in a situation where there isn't sufficient airflow. So this is the response of CO2 compared to time for a meeting. So imagine you're in a meeting room. There's one window in it, and it's closed. There's a table around in the middle. There's like 8 chairs around it, and there's far too many people in that space. The door's closed, and it's a little bit warm in there. At the start of that meeting, at 0 minutes in, everybody's filed in there and just about sat down and figured out what's going on and who's got a coffee and things. And the CO2 level, the carbon dioxide level in there, is about equivalent to what it's going to be outside. So it's sitting under 500 parts per million. But as the meeting goes on, things are being presented, something to do with the future, something to do with the past. There's probably a graph in there. There might be a whiteboard or some marker pens. The CO2 is starting to rise and rise and rise as people are breathing in and out. And by sort of 45 minutes into that meeting, we're at maybe 1,300 parts per million in there. Everybody's starting to feel a little stuffy, like the concentration's just slightly going on that one, and feel like your brain's a little bit fuzzy. But there's still stuff to cover, it's still going on. And by sort of an hour or so into there, the CO2 levels start to rise to about 1,800 parts per million. Now, this is definitely, you're starting to feel drowsy at this point. You're really not working at your best. Unfortunately, about this point, somebody usually says, shall we stop for a break? And the door opens, and the air flows in, and you walk out into the fresh air, and suddenly you feel a lot better. And it's not because the subject in the meeting was making you feel sleepy, it's because the amount of CO2 in there was rising. Now, I'm going to say that there's absolutely nothing dangerous happening here. You can sit for 8 hours in an environment of 5,000 parts per million with absolutely no ill effects whatsoever, but you won't be working at your best in that. And if what we're looking to do in terms of comfort in a space is we want to be able to be starting to make adjustments to the airflow as the parts per million of carbon dioxide raises above about 1,000. That's the point where we want to be doing something like opening a window or increasing the ventilation and start to be able to bring that CO2 level back down so that everybody's feeling okay. All right, so we've got a direction, we've got a sensor that we can use. How are we going to start putting that together? Now, fundamentally, I'm a design engineer. I'm like a magpie. I want to pick bits up and put them together and make new things. So I'm going to instantly disappear down a direction path where I'm looking at what sensors can I use and what parts can I use, what microcontrollers, what does it need to do in the middle, what battery life can I get out of it. And if this was sort of 4 years ago or something like that, that might be the right way to go, like this one on the left, which was a build from, I think, 2017. But we don't need to do that for a CO2 sensor. It was a distraction. You can go next door. There's a whole wall full of devices that are going to be able to do what you need. So it's probably easy in this case to be able to pick up off the shelf. It might look better to be able to do a self-build. It might look like it's cheaper, but ultimately they're only cheaper if you don't value your own time. And if there's an off-the-shelf solution that's going to do exactly what you need, I'd want to have a really good reason to not pick that before going down the self-build route. Now, we've used a few of these. I'm actually interested to see the Ascensus Eco that I saw about yesterday. We used the tabs ones up there. Actually, the one we picked for the office was the MileSight AM300. It does CO2. It's got some extras on there, but that's not important for this usage. But the key bit there actually was the e-ink display. Rather than just being a white box on the wall, we picked that one because it does provide a readout to the people who are in the room right then. So we might have a situation where we don't have to use the internet, and somebody who's in the room can see what's going on and take a decision based on that. So job done. Or not really, because collecting the information isn't enough. That doesn't match the requirements we had at the beginning about being able to maintain the comfort in that room. All we've done is take the sensor, pick to reading up. If we want to be able to make some choices with it, we probably need to get it off that sensor and start to make a connection out to somewhere else. So how should we connect this CO2 sensor and get data out to the internet? It may not surprise you, based on where we are, that the answer in this case is LoRaWAN. We're at a LoRaWAN conference. I did pick an example that was a good use for LoRaWAN, but why LoRaWAN? What are the decisions that mean that this is good for LoRaWAN? Now, I've got four kind of drivers on that one. We're looking for availability, we're looking for data, we're looking for power, and we're looking for distance. In terms of availability, I want this to go in our office. Now, we have Wi-Fi in the office, but we do IoT development. We already have LoRaWAN gateways in there anyway, so I've got coverage for both of those. So I can choose both those options really nicely. In terms of data, this is a sensor that's sending information up to the internet most of the time. I don't need to go down and connect, give it any instructions. So it's the kind of situation that LoRaWAN specifically was designed for. I'm taking readings every 5 minutes, 15 minutes, 60 minutes if they're not changing very much, and just sending them upwards. So LoRaWAN works nicely for that. But if I was doing something like once every second, or I wanted to be able to send commands back down again, then I might be looking at different options like Wi-Fi or Bluetooth. Then in terms of power, this is a device that's going to spend most of its time asleep, wake up, take a reading, send it out. But I'm putting it into a room that already exists. I don't want to try and find mains to be able to put it in, so I'm looking at battery-powered sensors. And in doing so, I want to get a connection solution that's going to use the lowest amount of power possible, so those batteries last as long as possible. In a different situation, if you've got a big battery, or you're recharging it every day, or you've got mains power, something like Wi-Fi or cellular might allow you to send, might give you the options to be able to send more and accept that it's going to use more power. And the last bit there is going to be distance. So I've got a single sensor in a single room that's actually fairly close to the gateway, so I've got a lot of flexibility in that one. But realistically, by picking LoRaWAN, I could add extra sensors into that room, or even actually extend it out to other rooms in the same building and be able to just add sensors to those with no problem. If this was a situation in which I'm going to want to go around the country, then something like cellular might be better, or as the satellite LoRaWAN solutions come online, there might be some other options there. Or if it's a situation in which the sensor is going to be no more than maybe 2 meters from a mobile device, something like Bluetooth is going to do really well in terms of that short distance. And then, so we've picked LoRaWAN, we've got a sensor, we send it up to the internet. Where is that information then going to go? Now, in the first state, it's going to go to the Things Network, because I've got a Things Network account, and I can send it up, and it appears the right place where I want it to. The LoRaWAN network stack job there is then to receive the message, to sort the message, to decrypt it, and optionally to be able to translate it from its radio form into a nicer form for us to be able to pass on to somewhere else. But there is an advantage that we get from LoRaWAN that isn't immediately obvious, and that's security of that data in transit. If you're not thinking about the security of what you're sending at this point in the project, then you're going to already have forgotten it later when it starts to become a problem. And the two things that I want to know from a remote device is that the information that it's sent hasn't changed in transit, and the information that I'm receiving has definitely come from my device and not somewhere else. Again, one device in one room isn't going to cause you a problem, but when you start making automated decisions on that, you want to be really sure that it's your information that you're getting from your device. And one of the things that I do see is that it's not always immediately obvious that it's the LoRaWAN network stack job to receive, to sort, to decode, and transfer those messages on. It's not the network stack job to store it. That data still needs to go somewhere else. It needs to go to somewhere where you're going to deal with it. So, where does that data go? For me, it doesn't really matter. The technology is sort of a distraction on that. It doesn't matter where it's going to, as long as it's something that you're comfortable with. It could be a server, it could be a VPS, it could be AWS, it could be Azure, it could be a droplet, a microservice, a Docker container, whatever it is that you're comfortable with. Personally, I've done a lot of stuff with Linux on the command line, so that's going to be my starting point. If I'm in a development environment, it's probably a Raspberry Pi that's sat on my desk. I'm not going to send it to my computer because I want to have a device that's always on and it's going to sit in the background doing its job. If it was going out to deployment, then it's going to be a server with some hardening and some backup to make sure that I've got some data security in there. Once it gets onto that, or to get it onto that server, I'm then going to need to be able to store that data and make some choices with it. My go-to, especially for development, is the GIN stack, the GIN, so that's Grafana, InfluxDB, and Node-RED. I'm going to be taking MQTT messages from the Things Network, excuse me. I'm going to be feeding those into Node-RED so I can translate them and place them into a database. Because what we've got is time-stamped data, so each read-in comes with a timestamp for when it's taken. I've got time series data, and a database like InfluxDB is going to work nicely for that, for being able to store it, deduplicate it, and make sure I've got some nice ways of giving it back out again. And then I can add something like Grafana as a front end to be able to create some nice graphs and see what's going on. And we get to the graph stage. This, for instance, is the CO2 readings from our office in February. And you can see the 5 days in the middle there and the weekends at either end. So you can see from the sort of 9:30 to 5:30, the CO2 level rises from its baseline around 500-ish parts per million, like outdoor air, up to about 850 parts per million at the peak. So I'm happy with that one. We could increase the ventilation a little bit, but it's pretty good. For instance, if you wanted to have a look at the digital twin in here, we're about 1,100 parts per million in here, so at the point where you probably would want to start increasing the ventilation, although from the last couple of days it started to drift back down again, so that's not a problem. And this is the point where a lot of IoT projects stop. We've got a nice graph, we can see what's going on, we can monitor it, but we haven't actually solved the requirements at this point. the requirements being that we want to be able to change the ventilation based on what's going on in that room. All we've done is moved the measurement from the room to the internet, and to be able to make any choices, we're still going to have to go somewhere, look it up, and make an action. So how do we then go from here to making an action? Now, for actions themselves, they want to be two things. They want to be timely. It's no good if you're waiting 6 hours to get information on what you should do right now. And they need to be actionable. There's no point telling somebody about something or instrumenting something up if there's no reason why they should do anything. If I get an email and it's not something for me to do, it's not something I can work on, it's not an action that I can use. So depending on the situation you're in here, it might be that you are sending a text message to a building manager so they can make an adjustment to the flow level in a room for air usage. I suppose the gold standard on this would be to be in a situation where you can open an automatic window opener, or you can adjust the fan speed to a room automatically. In our situation, we didn't have access to those systems, so what we did was Grafana will ping out an email to all of the people who are in the office when those readings go above and stay above 1,000 parts per million, so that somebody who's the first to get that one can stand up, walk across the room, and reset the fan speed in the office back from when the central system has set it back to 0 again from in the weekend. Now that does get us to a solution that meets the requirements. Not a perfect one, and there are some improvements that would be nice if the situation was slightly different, but definitely a solution that allows us to maintain that in the office. So, in conclusion there, let's run through what we've covered. First and foremost, you want to start with the requirements for the project that you're building. If the requirements for the project are things like you want to show off a specific technology, then it's fine to be technology focused on there. But if what you're trying to do is something for a person or for another output, it's important that you've got those requirements at the beginning so you don't get distracted and disappear off down a shiny route or something interesting. Then those requirements are then driving the hardware selection and the connection that you're going to use, if IoT is even needed in that situation, and then how you're going to route that data, how you're going to collect that data, and crucially, what needs to happen with that data at the end so you get the benefit of the system that you've spent so much time doing and building. Thank you. I am here for questions later if you want to run through some options as to how your idea might work. It's kind of the most fun part of my job, is coming up with ideas to things on the fly. So thank you very much.
Thank you very much, Patrick.
Okay.
I also like that you didn't just give up on the project because you can't automatically change the thing. You have human intervention in the end, I think.
It ultimately was a limitation, but it was, yeah, we have to have a human in there right now.
Yeah. Well, I like it nonetheless. Another round of applause for Patrick. Thank you so much.
Okay.
So we're going to take a tiny break for a couple minutes, and then we'll be back talking about how we give our LoRa devices eyes and ears. So that should be fun. See you in a bit.
A smile and it's like you're here. You taught me how to love myself and